Hi, everyone. Thank you for joining us today for our webinar, Sustainability and the Built Environment. I'm Molly Morrow, and I'll be your moderator for today's presentation. Before we begin, I'd like to quickly go over a few logistics. If you have any questions or concerns throughout the webinar, you may submit them at any point during the presentation via the Q&A or chat feature at the bottom of your screen. We will address these questions live at the end of the presentation. Also, just a quick disclaimer, the information provided in this webinar is not to be used as a substitute for professional engineering design and/or documents required by building code, contract, or law. Please refer to the manufacturer's specific application guidelines. Additionally, we will follow the webinar today with a survey. This is your opportunity to provide us with feedback on how we did today, ask any additional questions you may have about the topic of the webinar, or suggest new topics for webinars you'd like to hear in the future. And with that, we'll dive into an introduction, and I'll hand this over to our presenters.
Hi, good morning, good afternoon to you all. Thanks for joining. My name is Erin Valley, and I am a sustainability technology leader here at JM. I'm new to JM. I've been here about 4 months, but I have 12 years of experience in environmental management and sustainability across a variety of business sectors. So here at JM, I report up to our Chief Sustainability Officer, and I'm responsible for helping implement our sustainability strategy, which covers programming across our 4 core values, which you can see at the bottom of the screen: people, passion, perform, and protect. And that means we care about the health, safety, and well-being of our people, community impact, product stewardship, and work towards reducing the impact on the environment through monitoring carbon emissions, climate action, resource use, and circularity. And I'll toss it to JR.
Thanks, Erin. So my name is J.R. Babineau. I'm the Senior Research Manager for Building Sciences here at Johns Manville. I've been with JM for 28 years, and I sit and report up under our Corporate Research and Development Group. My background is really in doing research for things around building science, energy efficiency, acoustics, indoor environmental quality, really how buildings perform well, how sometimes they don't perform well. And all of that with an eye towards, product development and application development for building materials, right? For things like insulation, roofing, building enclosure systems, PV monitor, solar mounting. My background is I've got degrees in applied physics and engineering management, and I have a mechanical engineering license here in Colorado. And I think with the next, I'm going to also touch just real briefly, right, as we get started. So what are we going to talk about today? Right, first, Erin's going to kick us off in just a minute. We're going to get kind of a high overview of what is sustainability. We're going to be talking throughout about what's the value of a sustainable building and what are some of the best practices that sustainable buildings would employ. Also, we're going to touch on, right, what is embodied carbon? What's the value of a life cycle assessment? And I would say throughout, we're going to be talking a bit about the role that product manufacturers play in delivering sustainable buildings. And I think with that, we'll turn it back over to Erin.
All right. Thanks, JR. So my job today is really to set the stage for the importance of sustainable buildings. Why do we care? So to do that, I'm going to take us back to where it all began. Scientists estimate the Earth was formed around 4.5 billion years ago. And since that time, our planet has been figuring out how much life can live within it. So for millions of years, the Earth was uninhabitable to life as we know it today: fiery volcanoes, extreme temperatures, toxic air. But with time, things settled and the oceans and continents began to form. Around 3 billion years ago, life on Earth was first formed in our oceans with bacteria, algae, and jellyfish. And there was seemingly no limit to the growth at this time. The oceans were a blank slate of opportunity. So we saw many marine species proliferate in our oceans, and jumping forward in time, we start to see invertebrates, sharks, and fish. So the oceans are now teeming with life. A few opportunistic creatures with the right adaptations, made it out of the oceans and into a new world, life on land. So then we see reptiles, dinosaurs, and soon birds proliferating, growing, and developing into new habitats across the planet. So as all this life is developing, there is a push and pull between the natural resources on Earth and the life living on it to figure out how much the planet can support. So before humans made their grand entrance, there were 5 major extinction events caused by changes in sea level, ocean chemistry, and atmospheric conditions, among other things. And these extinction events impacted marine species, reptiles, and the infamous dinosaurs. It wasn't until after the 5th extinction event that mammals were able to make their moment in the spotlight, paving the way for humans to make their entrance. So looking back at this timeline, human history is just a blip in the history of our planet, and Earth has 4.5 billion years of experience of what makes life sustainable. So let's fast forward now to the rise of human civilization. For hundreds of thousands of years, humans were hunters and gatherers, living with the land, moving to where resources were bountiful. As nomads, we had to understand the natural systems we lived within in order to survive. We are smart creatures, though, and soon learned how to manipulate the land to our advantage. Agriculture was developed around 12,000 years ago when we learned we could grow and cultivate crops in one location, making the nomadic lifestyle obsolete. So as humans benefited from the advent of agriculture, cities started blossoming. The first known city was developed around 6,000 years ago, and from that point forward, the human population began to grow exponentially. At the height of Egyptian civilization, there are around 5 million people on Earth, then 50 million around the Roman Empire, 80 million in the Middle Ages, and then came the Industrial Revolution. The technological inventions of this time allowed us to harness the power of Earth's natural resources and make urbanization possible. Gone were the days of agrarian economies, and now we have machines, factories, and large-scale industrial production. And thanks to the Industrial Revolution and urbanization, the human population had now hit 1 billion people. So while the Industrial Revolution was a massive breakthrough for human society, we soon learned of the unintended consequences of unbridled growth. Here are just a few key historical events since the Industrial Revolution that turned our eyes back towards the natural systems we depend on. In 1892, the Sierra Club was established due to rising concern of environmental degradation and pollution from industrialization. In the 1930s, there was the Dust Bowl, caused by unsustainable agricultural practices, leading to the creation of the Natural Resources Conservation Service. In 1952, across the pond, there was the Great Smog of London, caused by air pollution from burning coal, resulting in the deaths of 12,000 people, leading to stricter air quality regulations in England. In 1960, the Cuyahoga River caught fire from severe water pollution, leading to the passage of the Clean Water Act. In 1962, Rachel Carson published Silent Spring, which sounded the alarm on the events of industrialization on the environment, led to the creation of the Environmental Protection Agency and the Endangered Species Act, and is well known to be one of the reasons why we were able to save the bald eagle from the brink of extinction. And then one more event, 1970, improper disposal of toxic chemicals into the Love Canal led to the creation of the environmental justice movement and the Superfund program to clean up hazardous waste sites. So since the 1970s, modern day society has realized that we are in fact interconnected to the environment and everything we do has a cause and effect. We began to regulate industrial actions, and in 1972, we see the first use of the word sustainability in reference to the future of humanity. So back to the word sustainability. It goes by many names, has many uses, many meanings. You may see sustainability referenced as the triple bottom line, or people, planet, profit. You may see ESG, or environmental social governance. But what we're really trying to hone in on here is that human society cannot thrive without a viable planet, an equitable economy, and bearable living conditions. So now, where are we today? We are now a population of 8 billion people. So in just 200 years, we have grown by 7 billion people. Human society is now largely defined by industrialization, urbanization, and globalization, and we have a high dependence on the built environment. In order to support 8 billion people on this planet, we have to reconnect with the natural sources our society is built on. So that brings us to sustainable buildings. Since 1980, many architecture and engineering leaders have recognized the importance of maintaining harmony with our natural ecosystems, and several buildings and standards approaches have been developed. The logos at the bottom of the screen give you an idea of just how many programs have been developed. And in 2002, the World Green Building Council was formed to unify and support national and regional green building councils. So before I hand it back over to JR, who is our resident expert in building science, I'm just going to walk through a few more key details on how we can achieve sustainable buildings. So first, looking at sustainable site selection. Is where we build disrupting natural habitats? Do our sites connect to existing infrastructure? And do we positively contribute to the community needs of the area we're building in? Energy efficiency. How can we design the building to minimize energy use? What is our source of energy? And are there building controls that can facilitate more efficient management? Indoor air quality. This one's important because on average, humans spend approximately 90% of our time indoors. So we want to make sure the indoor environment supports human well-being. So that means paying attention to ventilation, chemical exposure, lighting, acoustical conditions. Water conservation. How can we reduce water usage in our buildings? Is rainwater harvesting available? Gray water systems, something we can consider? And can we landscape with plants that have low water demand? Material selection. What is the environmental impact or embodied carbon of the materials we're building with? And are we building something that's durable and long lasting? And lastly, waste management. How can we plan construction and demolition to minimize waste sent to landfill? And can we use recycled or reused materials within our structures? So with that, I will pass it back to JR.
Awesome. Thank you, Erin. So to dive into a little bit more about kind of what constitutes a sustainable building, we're going to first look backwards, right? We're going to look at how we used to build buildings, and but this time through this lens of these 6 aspects of sustainable development, right, that Erin just described. So if we start on the left, right, this is a 1,000-year-old church in Ireland. It is made out of dry stacked field stone, right? And if we look at it through this sustainability lens, right, we would say, well, right, it gets some high marks, right? The impact on the site is pretty low. It's not heated and cooled, so it doesn't use any energy. Right, the materials that were used are all local, right? There's not much impact to water. There was probably not a lot of waste. But on that last piece, indoor environmental quality, right, it's terrible. You wouldn't want to be in this building, on a chilly, damp Irish winter. Right, kind of jumping ahead several hundred years, right, to the next image, right, we start to see that we start making some improvements, right, at least certainly to the indoor environmental quality, right, it's better, right, but now we start raising some questions around, energy use, right? So this building is clearly heated. We see a chimney coming out of the roof, right, but that likely was burning wood or coal, right, which we know, can have some severe sort of pollution effects, right? The materials for this building were probably locally sourced, and fairly sustainable. Water use, again, related to this building, it doesn't house probably a ton of people. But again, right, instead of these green check marks, we start seeing question marks. And then as we move forward to these last 2 photos on the right, and more modern buildings, right, we realize that right, the impact on the site to build modern buildings can be significant. Energy use becomes kind of a question mark because it depends just on how well the building was designed and how it's using energy. Materials, often, of course, right now we bring materials in from sometimes very far away, right, around the world even, to build our buildings instead of things that are more locally sourced. Again, water, right, could be a red X, could be a question mark. Same thing with waste, right? Construction waste is a real big problem and something that's trying to be, actively addressed, especially by a lot of various sustainability programs. Right, the one kind of check mark, clear green check mark in modern buildings tends to be indoor environmental quality. Right, we do a better job of protecting ourselves from the weather, but overall our impact on the environment becomes more extensive. But right, we do have these more complex sustainability issues, but right on the plus side, um, we also have um, right, more materials, more tools, more solutions, right? Improved designs. If we start here on the left again, improved designs and materials can lead to much better energy efficiency, right? Better insulation materials, better air sealing, better windows. Um, right? We've got technology now that enables us to have renewable energy sources that can sometimes be on the building itself, right, or offsite, but we can avail ourselves of energy sources that have far less impact on the environment. Through thoughtful planning, right, we can allow ourselves much less site disruption, and we can maintain now, or we do a better job of maintaining things like an urban tree canopy, right? Shade is one of those really important things from a site development and livability perspective for the urban environment. Same thing with better water management, right? Technologies like permeable and porous pavements, and also just better water reclamation and management within buildings themselves, right, lead to better water management. And finally, we can do all of this without necessarily sacrificing indoor environmental quality, right? We can still deliver good indoor air, we can deliver good access to daylighting, good acoustics, all of that are still possible. It all just requires, right, um, good planning, good design, and just a project team that's kind of committed to these goals. So next, right, we're going to touch on some best practices, and in particular, right, as the words here in parentheses say, where insulation can help, right? So we're Johns Manville, we're a building products company, but one of the focus really today is around insulation. And so that's kind of going to be the slant that we take a little bit. So as we've already mentioned a little bit, right, the six sustainable design aspects, this is a big topic. We could easily spend hours digging down into each of these aspects, talking about the options, how to meet these various goals. But what we're going to do today with our look is we're going to first look at this graphic on the right, which describes the aspects of a sustainable design, but now from the perspective of how the building is designed and built and the impact on both the design goals and the budget. So the point here is to emphasize that factors like building shape and orientation can have really big impacts on sustainability goals, while usually having the smallest cost impact, since these decisions are often made while the building still only exists on paper. Right now, admittedly, sometimes the site itself dictates some of our choices, but maximizing these items can have some really big benefits. Next are the passive measures, which are these static aspects of the site and the building itself. And insulation really falls squarely into this category, especially in the design phase. Passive measures, right, such as insulation, can have a really big impact with only moderate cost impact. And finally, right at the top of the pyramid are the active measures. So these are technology features that tend to be shiny and exciting, but the reality is that the impact of these measures is often limited, while also usually coming with the largest price tag. And this is often happens because sometimes we're asking these active measures to kind of make up for other trade-offs or maybe mistakes or oversights that could have been better addressed, right, lower down on the pyramid. So from an insulation perspective, right, the bullets on the left, right, what we're going to really focus in on a bit today is one, energy, right, which from a sustainability perspective, you could read as operational carbon, right, carbon emissions of the building in use. We're going to talk about indoor environmental quality because insulation plays a big role there. And then finally, we're going to hit on materials and resilience, which is actually isn't even one of the things that we, right, was in the 6 aspects, but resilience is really just this idea that, right, a building that lasts longer is a more sustainable building, right? A building that is junk in 10 years, it's like, well, why did we even invest the resources to build that building if it's only going to last that long, right? So resilience becomes an important piece too. So energy use in buildings. So, right, this is just the obvious area, right, where insulation helps meet sustainable design goals. So to start, we're going to go back to last year. I gave a webinar around how to reduce energy use in buildings. And what I've done here is I've combined data from, on the left, residential buildings in the US, and on the right, commercial buildings in the US. And then I just clicked in, right, these kind of highlighted areas. And what we're really trying to remind us all, right, is that still today, right, heating and cooling makes up 50% or more of the total energy use for both housing in the US and for commercial buildings, right? Even though commercial buildings are far more varied, right, and have a lot of different other loads, but just to heat them and cool them still is around 50% of all the energy use. If we dive a little bit more now here into residential buildings, sorry, I keep losing my mouse. There we go. Right, so focusing on residential buildings, these heating loads are mainly driven in homes by air leakage and heat loss through walls, ductwork, floors, and ceilings, right? Similarly, the cooling loads are impacted by heat gains through walls, ducts, floors, ceilings, plus, of course, solar gains through windows, right? But the highlighted areas on these bar graphs are all spaces where good insulation, good air sealing can make these sections, these pieces, get smaller. On the commercial building side, right, of course, it is more complicated, right? Mainly because of the wide variety of shapes and sizes, and also because we use our commercial buildings, right, in a lot of different ways. And so the pie charts on here show the contributions to the heating and cooling loads. And just so that we're aware, right, these pie charts kind of combine together all of the data from all different types of commercial buildings. So that tends to kind of, right, muddy the picture a little bit. But if we first look at the heating side of things, at least on the heating side, it's pretty easy to see, right, walls, roofs, floor, the ground, air infiltration, right? Again, those make up almost half of that pie chart. So insulation, again, directly impacts all of those. If we if we look at the cooling side, the cooling pie chart, right, that's a little bit more unclear, right? The little gray cross-hatched wedges kind of suggest that the like walls or windows might actually help with cooling load on a commercial building, but that's not really true. If we click in and if we look a little more, in depth at, just some examples of some specific types of commercial buildings, we see that it's a little bit different, right? So if we start here on the left, if we look at a school has a lot more building envelope, right, and a lot less core. And so the heating load for most schools is about 3 times the cooling load. And again, in the pie chart, we can see, right, that insulation would help a lot with walls, roofs, the ground, air infiltration, right? All of those pieces are important parts where a good insulated building envelope is going to help reduce the amount there. However, if we look here in the middle at the hospital, right, the pie chart showing the cooling load of a hospital is significant because the cooling load there is about 30 times larger than the heating load. And that's dominated by things like equipment and lighting. And similarly, for a large office building, the cooling load is about 10 times the heating load, again, dominated by lighting and then solar loads through the windows. But it doesn't mean that we don't need insulation in these buildings, right? If we didn't have insulation in these buildings, especially in the building envelope, the exterior parts of these buildings would just be uninhabitable. And also, these cooling and process loads, right, really drive a big need for mechanical and HVAC insulation to help those systems operate more efficiently. And finally, and Erin kind of touched on this earlier, and I'm going to touch on it now, especially big commercial buildings like offices and hospitals. What these big complex buildings really mean is that oftentimes parts of this building might be calling for heat while other parts of it might be calling for cooling on the same day at the same time. And that presents a lot of challenges, both for just building operating systems, right? The system needs to be smart enough to know what different parts of the building need, but also then right, from a sustainability perspective, it means that sometimes it's very difficult to avoid, expending energy because of the function that the building performs, and we need to be sure, right, that our meeting our sustainability goals doesn't mean then the building can't do the thing it's there to do. So we've been, talking about this now for a minute. Obviously, we need insulation in the building envelope. From a sustainability perspective, a well-insulated and well-air sealed envelope really sets the stage for delivering not only on energy and carbon reduction goals, but on everything else, right? From indoor air quality to acoustic comfort to resilience. And we'll get into those in a minute. For a good building envelope, right, specifying things like insulation R value and envelope air tightness are clearly needed. And I'm not going to really go into, right, what R value do you need, because that really varies a lot depending on the building itself and the climate that we're building the building in. But right, the designs and the specs are only part of it. We need to make sure that what gets designed can actually be built in the real world by humans. And that's where this image down here on the lower left comes in, right? Mock-ups on the job site. Right, this is really important to make sure that contractors can successfully implement whatever it is that we want them to put in. Same thing goes with commissioning. Right? We want to be sure that commissioning and testing happens, even not just in the mechanical systems, but of the building envelope, so that we can be sure that what was specified was actually installed and that it actually works as intended. And I think it's really important to emphasize here that these aspects of the building envelope, right, insulation, windows, cladding, air sealing, often are there for the life of the building. So investments that we make now in materials and attention to detail pay returns for decades. On the mechanical insulation side, I'm sorry, there we go. Right, insulation plays a very important role too. And for this, we've got an example to share from a study that was conducted by the National Insulation Association. So our exercise here, if we start on the left, right, we're gonna look at the amount of carbon emitted by one full-size pickup truck driven around 20,000 miles a year. So it emits about 18,000 pounds of CO2. And if we wanna say in our building, how can we make sure our building doesn't emit that much, right? We're going to offset that amount of carbon through savings in our buildings. And so we've got some options that we could go through. So first at the top, we could replace just over 300 incandescent light bulbs, right? 40 watt or so. If we replace those with LED bulbs, right, that could offset on average, right? Of course, it depends on the sort of emissions for your electricity, but assuming kind of average emissions for the US, just over 300 light bulbs, or we could plant 360 trees, or right, I think the powerful option here is to show that if we just insulate one 8-foot long section of pipe. Now, this particular pipe, right, the photo shows somebody like insulating some water pipe. So this is a bigger pipe. This would be like a steam pipe. So 4-inch long, 4-inch diameter pipe operating at 350 degrees. If we insulate it with just 2 inches of insulation, that right there will save the equivalent of what that pickup truck emits every year. And you might think, 350 degrees, how often do we run into that? That sounds more like an industrial process. There are some systems in a big commercial building, right? Steam systems that could operate at that high temperature. But even just thinking about a regular sort of boiler, right, that operates at between 212 and 250 Fahrenheit, and instead of one section of 8-foot pipe, maybe we need 3 or 4 of those sections. That's still not a lot, right? There's hundreds and hundreds of feet of this pipe in a building, right? So these savings that we get, they come in quick. And remember, these savings are in 1 year, and this insulation delivers every single year as we go along. So to kind of wrap up on the energy piece, right? For both residential and commercial buildings, reducing energy use and, of course, in turn, reducing operational carbon emissions, insulation is a key factor. And just like every other conversation that we ever have about building performance, we have to remember buildings are interconnected systems of systems. And too often, what we still see in buildings is that they get built with a junky envelope, with air leaks, poorly installed insulation, thermal bridges, and then we kind of try to make up for it with these highly efficient HVAC systems. And the problem is that these great systems, they just won't deliver the savings we think they will, and often won't even work well when paired with poorly designed building envelopes. So let's not do this anymore, right? Um, instead, the right priority is to first minimize the loads from the climate that the building sees in the first place, and by specifying a good envelope, and then we can specify, right, these really efficient HVAC systems to meet the remaining heating and cooling loads. And not only does this get us the most savings and the most carbon reductions possible, but then this HVAC equipment, like heat pumps and high efficiency furnaces, they actually work better and last longer when they are paired with a good building. All right, next, we're going to turn our attention to indoor environmental quality. And while insulation doesn't have an aspect or have an impact on all of the elements listed in the slide on the bullets, I wanted to kind of list them out because oftentimes indoor environmental quality gets kind of conflated with just indoor air quality. However, right, IEQ is much more than just good indoor air. It includes thermal comfort, acoustics, lighting, even things like aesthetics and other factors, right? But insulation does directly impact these first three. So indoor air quality, right? You might think, how does insulation help with good indoor air? And so, first off, as one of the materials that's in the building, insulation does contribute to the total load of pollutants or, volatile organic compounds that might be in the building. And even though most insulations emit a tiny fraction of the VOCs that might be emitted by furnishings or finishes, right, product manufacturers like JM, that's an important piece. We still design and test all of our insulation products to be low emitting and often formaldehyde free as much as possible. The other aspect where insulation comes in on indoor air quality is for air sealing, right? A lot of insulation materials, especially things like spray foam and foam sheathings, help with air sealing, right? We want to be sure that the air that we are breathing in our buildings, that it's brought into the building on purpose, right? It's filtered, it's tempered, it's delivered by our HVAC system. We don't want to be breathing air that's just pulled in through random gaps and cracks and holes, right? It's going to be flowing in over, dirt or ick or whatever. right? That's not the sort of air that we want. And so air sealing is really an important part of that. Thermal comfort is an aspect of the indoor environment that insulation actually plays a really big role in, maybe bigger than you're aware. So you might not realize it, but that thermostat on your wall is only partially responsible. And by partially, I mean like less than half responsible for how comfortable you are at work and at home. Actually, the temperatures of all the surfaces around us have a very big impact on our comfort. So if we look here at the graphic on the right, if it's cold outside and we're in a poorly insulated space with cold surfaces, we'll feel cold, even if that thermostat on the wall thinks the air temperature is just fine. We are going to radiate heat away to these cold, uninsulated surfaces, which leaves us feeling cold too. Even worse, big cold surfaces like this bad window that we've got in the drawing, can actually chill the air that's next to them, and that cold air then will fall down and spill out over the floor and makes our feet cold. So we kind of even think that there's a draft sometime when there's not. Um, But if we instead a properly insulated space, then those surfaces that look at us, if they're much closer to the air temperature, then we actually will feel more comfortable, and we can actually often even reduce the thermostat setting and still feel comfortable, That's how big of a role, the surrounding surfaces are. Insulation, if we look at the little graph on the image on the left, insulation for heating and cooling systems plays another really important role in thermal comfort. So we've got three examples here showing examples of a piece of ductwork passing through a ceiling plenum, like in a commercial building. And if the plenum is at 80 degrees and we have 100 feet of duct running through there, the middle drawing is for the bare uninsulated sheet metal duct. The air in that duct will heat up by over 9 degrees as it's passing through this 80-degree space, So then we want that the air that's delivered to the room to actually be as close as possible to the temperature it was when it left the heating or cooling equipment. So if we insulate this duct instead with either some duct wrap, or if we replace the sheet metal with duct board, any of those sorts of options, so the upper and the lower drawings really means that now that delivered air warms up by less than 2 degrees, So we're actually delivering air to the room, and it can do its job of conditioning the space rather than, some random building cavity. Finally, acoustics. Acoustics is, I don't know, anybody who's ever heard any sort of other JM webinars has probably heard myself or my colleagues talk about how insulation helps with acoustics, and it really does it in a ton of different ways, Acoustics is just important from an environmental quality perspective because noise impacts our well-being, it impacts our work productivity, it impacts how well we learn, all sorts of things. And insulation helps in a number of ways. First is, again, related to heating and cooling systems, HVAC noise, We don't want a ton of noise dumping out of our registers along with the air. And products like duct liner and duct board and just HVAC equipment insulation all help reduce the amount of noise that comes down the duct runs and eventually gets dumped out into our spaces. Next would be sound isolation. Insulation plays a critical role in reducing the amount of noise that can go through walls and floors from a noisy space into spaces that we want it to be more quiet. Without insulation, it really limits the amount of noise that a wall system can block. And then finally, reverberation time. So this is controlling echoes in a space. If we think about, being in a space like a recording studio or your bedroom, versus being in, a big cavernous church, or as so often happens anymore, like a loud restaurant, So often these spaces are not really designed to control echoes in the space. And insulation is really the key way that you do that. The photo on the lower right, all those green panels up in the ceiling of that arena, right, are there to control the echoes in the space so that it's not quite as loud and echoey as it would otherwise be. Next, we have materials, right? So insulation plays a role in kind of material aspects through a couple of main factors. The first being recycled content. Many insulation materials have 25% or even more recycled content, right? A good example would be the top photos showing some recycled glass, and that turns into the image on the upper right, which is called glass cullet, which can easily get remelted and turn into things like fiberglass insulation. Other insulation materials also don't necessarily use glass, but use other recycled materials. Local or regional sourcing is actually a key part where insulation plays a role. Right, as I mentioned early on, one of the things that we would like to not be doing is transporting materials right across the country or around the world to build our buildings. And insulation is a good example of not doing that, because insulation is usually so light. To transport insulation a long ways actually becomes cost prohibitive, right? So regional sourcing is usually, almost any insulation materials you get are usually going to be made relatively close by. And then finally, embodied carbon is the other area, right? And of course, embodied carbon, all materials that go into a building have some sort of embodied carbon. And just to kind of touch for a minute, the way that is measured is through a process called a life cycle assessment. And a life cycle assessment really looks at any sort of building material that we use, and it looks at the energy and the resource impacts to, right, all the way from the raw materials, right? If we have to extract something out of the ground, right, to the manufacturing process, to the energy required to extract and manufacture a material. Right, and there are other aspects of LCAs that then also capture the energy and resource impacts to distribute the material, to install it, actually, its use in the building, and then finally even disposal, right? So there are aspects of life cycle assessments that cover all of these things. Most LCAs, or most environmental product declarations, which is the document that gets attached to materials, tend to only include this kind of what we would call cradle to gate part of it. So this would be right from, this would be like, again, the extraction, the manufacturing parts, not the later pieces. And here's where I would say that insulation is arguably a pretty unique building material, in that it is the one material that, using more of it, even though that means more embodied carbon in the building, ultimately reduces the carbon footprint of the building. And this is something that's been shown to be true across all building types and across all climate zones. So this graph has data in it. Well, the graph itself is also from a study that was performed by a consulting group called ICF. And what they looked at was the effects of insulation across all building types, residential and commercial, and it shows how long it takes to pay back the carbon embodied in the insulation itself through heating and cooling savings from the buildings, right? So now, this kind of usually raises a lot of questions, right? What is the baseline for the study? It did assume buildings with no insulation. You could argue that that's not really a reasonable baseline, but given the wide range of kind of code requirements across the US and the world, this was just kind of how they chose to do this at the beginning. For a given specific building, it would be very easy to redo this exercise, right? To look at like above code levels of insulation. But the important thing I wanted to show, so a couple things on the graph. So the different colors of the various dots, right, are for different climate zones. And so we see on the right, the bright orange, climate zone 1A, that's very warm, right? So the energy demands on most buildings end up being relatively low, even though there's a cooling load there, right? Versus climate zone 8, which is like Arctic, right? That's all the way over here on the left. So that's really showing that the payback period for insulation materials, right, as we go to colder climates, gets to be shorter and shorter. And the real takeaway here is that for the vast majority of insulation materials, the payback is less than a year, right? We can measure payback in weeks and months when we start including the use phase savings that insulation delivers, and it's just not something that any other building material does for us, right? Anything else that we use more of, that embodied carbon just kind of sits there and is just there for the life of the building. Resilience is kind of the next aspect that I wanted to talk about, and insulation plays an important role in a number of factors, things like disaster recovery, wildfire resistance, and a topic we're going to hit on called passive survivability. So real quickly though, disaster recovery really just gets at how well materials tolerate things like floodwater. Right? Or conversely, how easily that they are removed and replaced if they're damaged. So your insulation choices can sometimes impact disaster recovery. Wildfire resistance, on the other hand, is one that insulation can impact in a couple different ways. So the first is embers, right? Unvented attics bullet point. Embers being sucked into attics is a very common ignition point for homes that get lost to wildfires. And using strategies like unvented attics, like we see over here on the upper right in the photo, are often really chosen for energy savings, but they can greatly reduce this risk because now the attic space, right, is not pulling in any sort of outdoor air. A second insulation factor for wildfire resistant homes would be just fire resistant assemblies, especially if we're using things like non-combustible materials like mineral wool boards, right, used as continuous insulation, right? These sorts of materials can result in far more fire resistant assemblies than without those sorts of materials. And then finally, the last topic around resilience is passive survivability, which is really just this question of how long can we survive in a building if we get this combination of an extreme temperature event and a power outage, right? And as we've heard in the news over the years, like this happens actually far too often. So the table on the slide here summarizes a study published in 2023 by Pacific Northwest National Lab, one of the US Department of Energy labs. And the table focuses on new homes, though the study also did look at existing homes. And based on kind of the known limits of temperatures that people can tolerate, they were able to calculate how long an indoor space would be safe following a power outage using both cold snaps and heat waves from typical weather conditions across multiple US cities. Right, and the main takeaways here are to note that most new homes, especially in colder climates, right, would only be safe, right, a few hours, right, less than a day. If a cold snap, right, was combined with a power outage, like let's say right, a freezing rain or an ice storm, right, and even homes that were built to insulation levels in the 2021 IECC, while better, right, don't really give us the passive survivability that we might think that they would, right? Not until we get to homes built to the passive house standards, which are really insulated and super, super air sealed, do we start to see consistently, right, this days of safety metric where it's extended out, right, to close to a week. So, right, good insulation and air sealing is really key for passive survivability. All right, last two slides, we are nearly done, and then we can go to some questions. Right, first, I just want to touch again right back on LCAs and product manufacturers, right? I touched on it a little bit, but it's really important that if you see environmental product declarations out there published, right, that the LCA process that built those documents, that they should follow what's the PCR stands for a product category rule. So it's important to check, right, these documents when you see them out there in the world, that they were made following ISO standards, that they followed the PCRs, that they're using approved software tools. They should be third-party verified, right? These are important documents when it comes to specifying materials, insulation included, but really any sort of building material. And that even within EPDs and LCAs, there's kind of a hierarchy of quality, right? The best ones that you're going to find will be specific to both a product and the factory where it was built, right? That's the location specific piece. So, right, so a material built made at a certain location to have its own EPD, that's kind of the highest quality, right? The next one would be product specific, but from a manufacturer where they've probably averaged across their various manufacturing locations. And then kind of the most generic one, right, would be these where it's kind of for a product category using an industry average. And again, the reasons why we get variations in how detailed those get are many. Sometimes it's economic, sometimes it's other reasons in terms of data availability, but it's just good to be aware and to look at those sorts of things. And finally, last, right, just some of the main takeaways, right, from today, right? Our buildings have changed over time, right? They started off arguably pretty sustainable, but not very sustainable from a human perspective, right? Not very comfortable. So we've got our complex modern buildings, right? They are still these interconnected systems of systems. And when we make changes to one part, we always need to keep looking at what's the impacts elsewhere so that we avoid unintended consequences. Right, as we have talked about throughout, sustainable design looks at all of these, lots of aspects, right? Not only just how does the building work, but how does it interact with the environment and the communities around it, right? And the best examples really, coordinate and leverage these synergies as much as possible. I've got to say, right, I think we've hammered it home. Insulation is an important material. It impacts maybe even more areas than you might have thought coming into today's webinar, right? And not only that, but it's one of those materials that tends to last and be in place for the life of the building. And finally, we don't want to forget again that our buildings exist for a purpose. Sometimes I have personal examples where I've seen buildings be done where they're built very sustainably and use low energy and other things, but they inadvertently kind of sacrificed some functionality for that. And so we got to make sure our buildings deliver on their purpose and that they last, right? That they're resilient and aren't effectively disposable. And with that, I think I'm going to turn it back over to Molly to wrap us up and go into questions.
Thank you, JR. Thank you, Erin. We do have some questions that came in, but before we get to those, I would like to take a few minutes to go through some additional resources that we have for you. First and foremost, we maintain all of our informational resources on an online portal called The Source. You can get to this via jm.com, or if you want to scan the QR code to the right, it will take you to this online page. This is where the webinar will be posted within the next few days, and you'll also have access to our other recorded webinars, blogs, product documents, trainings, and tools. Also, for additional resources, I encourage you all to follow us on our Building Insulation social channels. We provide a wealth of informational resources on all three of these. And finally, for anyone who attended today, you will receive a certificate of completion after the webinar that may be submitted for professional development hours. This will be sent to you via email and should be in your inbox by next week. Again, a recording of this webinar will be posted on The Source within the next couple of days, and when it becomes live, we'll send you a link for direct access. So if you missed any part of the presentation or feel the content might be relevant to a colleague, you'll be able to access it on demand. And with that, let's take it into some questions. The first question is, how can building codes evolve to better support sustainability?
I'll take that one, I guess, or at least start with that one. So I think codes are That's an interesting question, and I would say there are some codes out there like the um, International Green Building Code, right, that really do try to kind of take sustainable aspects and put them into a code language context. I would say it's also honestly become a challenging and contentious issue over the last several years, as sometimes things like the energy code, right, has attempted to bring some, sustainability measures beyond just energy efficiency into the code itself, and then that's encountered some pushback. Um, so it's one of those that codes do play an important role, as far as getting things beyond just an optional choice, but it also requires jurisdictions to adopt those codes. But they do play an important role.
Great, thank you. I actually don't think we're going to have enough time to get through all of these, but I'm going to just keep going here and we'll get through what we can. How does JM work with its suppliers towards reducing the embodied carbon of their products?
I can take that one. So at JM, we have our own sustainability goals that help reduce the impact of our own operations. So we currently have a goal to reduce our scope 1 and scope 2 emissions by 40% by 2030. We also have a goal to reduce our waste intensity by 10%. And we have been working to minimize our waste intensity over the last 10 years. And that does help decrease the embodied carbon of our products. JR mentioned about recycled glass cullet. We do focus on circularity and utilize recycled glass cullet in our products where feasible. And through all of these efforts, that does help reduce the embodied carbon of the products we offer.
Thanks, Erin. Somebody wrote in saying they would like to hear about PMRA, inverted roofs / green roofs.
Okay, so obviously we didn't touch much on roofing today. That's a great question though, and green roofs. I guess when I think of that, I'm thinking you mean vegetated roofs, and they can play a really important role, right? Vegetated roofs help with urban heat island, right? Because they kind of like a white roof does on a building, right? They tend to reduce the temperature that's on the building. They can help from an energy perspective by reducing the cooling load on a building. And they also help with water management actually by reducing, right, slowing the runoff, right, that comes off the building roof. So they have a lot of aspects. Of course, because today we were kind of more focused on insulation and less on roofing, I didn't really touch on that, but I will kind of give you a teaser because actually I just recently heard from our roofing systems division. They are actually in the process right now of developing a green roof or vegetated roof guide that is going to be published this fall. So I would say check back at jm.com later this year, and there should be some awesome information out there.
Thank you, JR. Okay, we just got a question submitted. Why do we see in the commercial, but also the residential markets for insulation contractors to use much more needed mineral wool products based on the building specs?
I guess that's a good question. I mean, I would say there's a lot of reasons I get why somebody might be specifying mineral wool. From my personal experience, um, it's usually driven by fire, fire code, or not just fire code, but fire resistance. Right, mineral wool, right, is has a much higher melting point than fiberglass, and it's non-combustible, and so it kind of gives the most flexibility when it comes to fire resistant assemblies, and so we see a lot of it specified that way. Also, I have seen it specified, especially in areas like the Pacific Northwest, where it gets specified because it allows we're kind of getting into the building science of it. It allows water vapor to pass through easily. And so I see mineral wool specified on the exterior of buildings because it can freely drain water and it can insulate the outside of the building, but allow better vapor management, moisture management, I guess would be the right way to describe that. But so a lot of different reasons, at least from my chair.
Great, thank you. And I'm going to do one more since we are just at time right now. JR, I think this one will be for you too. How does the new material price out versus the old stuff?
Okay. So I'm going to paraphrase back what I think the question is, right? So I think where this question is going is that oftentimes, right, sustainable buildings get kind of labeled as being expensive, right? Too expensive, more expensive than a quote traditional building, that sort of thing. And so, from that perspective, I would say it doesn't have to be, right? I mean, from the insulation side, right, the exact same insulation materials, fiberglass, mineral wool, spray foam, board foam, that we've had for decades are the exact same materials that gets used in a sustainable building. We might use a little bit more of them. We might be a little more thoughtful in how those materials are applied, but the cost impact is actually moderate to zero often, right? It really just requires attention to those goals at the outset and good project team coordination. So, like that is a common myth. And I would say that, it's the shiny and the whiz bang things that we often bolt onto our buildings to try to then say that there's this sustainable bow on it. Those can be expensive. But I would say in general, to really deliver on a lot of the sustainable aspects really does not require a significant cost impact.
Great, thank you.
Mm-hmm.
Thank you so much to everybody who attended today. If you have any additional questions, please don't hesitate to reach out to us directly or via the survey that will pop up on your screen after the webinar. If we did not get to your question today, we will follow up with you after the webinar. Thank you so much for attending. Take care and enjoy the rest of your week.